Okay, Math 9, how you doing? Lesson 7-1, multiplying and dividing monomials. Okay, so we'll be looking at working with single terms, and this is important work because this leads to formula work, and formula work leads to algebra, and algebra is a huge part of the grade 9 year. In fact, it was a huge part of your grade 8 year too. All right, so what are the big ideas? Show off a few new tools here. Got some updates to this little program. Once you're done this, what you need to be able to do, well, first of all, I guess you need to be able to see me, don't you? So let's turn this on. There we go. And we'll go full screen. So what you need to be able to do by the end of the lesson is you have to be able to multiply terms and divide them. So get our pen tool up here, and I was going for an orange. There we go. We want you to be able to multiply monomials with other single terms, other monomials. And we also want you to be able to, I'll hit done there, so we can switch colors. We also want you to be able to expand on that. We want you to divide a monomial by a monomial. So think about it. As we lay out these topics, we're getting you to do it's formula arithmetic. So multiplying, dividing, adding, subtracting. In chapter 5, we did a heck of a lot of the adding and the subtracting. Well, that was going to, of course, lead to multiplying and dividing. And this all builds on everything we've done in the course so far. Your exponent rules become really important as we move on. Okay, so speak of the devil. There's the exponent rules. When multiplying similar bases, what do? So 2 to the fourth. Now, because they're side by side like this, what it means is they're being multiplied. 2 to the fourth. We'll use a dot to represent multiplication, because remember that an x is going to be used as a variable pretty soon here, times 2 to the third. So the product rule, when the bases are the same, this is 2 to the 4 plus 3, or 2 to the 7th power. So the rule, going back to our previous unit, was when you're multiplying the bases, you add the exponents. So if you're multiplying the bases that way, and you add the exponents, then it stands to reason that what you do when you go to divide, instead of adding, what you'll do is you will do the opposite thing, right? You will subtract the exponents. Go with a nice orange here. Turn that down a little bit. Ha, there we go. So that you subtract the exponents in the other case. And our example below, zoom in. The understood exponent of this 2, stop and think for a second as to what it is. Hit pause. Okay, well, if you're back, it's 2 to the first power. If you didn't pause, well, that's up to you, I guess. 2 to the first power. 2 to the 4 minus 1, or 2 to the third power. Now remember that this of course can be proven. Okay, so how do you know that that rule of subtracting the exponents works? Well, 2 to the fourth power is 2 multiplied 4 times divided by a single 2. If you cross out similar factors above and below, 2 goes into 2 one time, you're left with, well, look at that, 3 2's. 2 to the third power. So that would be 8, and below we get 8. So our rule is holding. Mathematically, it's sound. Now we're going to really kind of up the ante a little bit, and we're going to introduce these sort of shapes. We call these manipulatives. They're tiles, and what they're designed to do is introduce pieces of formulas. Okay? So we're go- in order to introduce a square, if you think about a square for a moment, a square is when two sides are exactly the same. So if we say that this tile represents, actually that's not going to show up. Let's choose a darker color. If that tile there, use a dark kind of a green there, if this is an X, then this is an X for width and an X for height. So we'll say that squares are X squared tiles. And we cut out a few of these in class, and we've popped them on the overhead a few times. Doing this lesson, I'll just be doing it obviously, working with my iPad here. And in your book, they have an interesting convention. An X tile is considered to be the longer one, so it's a rectangle as you see here, right? And here is our X squared here. So what if we have something different? What if we have our X tiles are understood to be X to the first? There is a slightly shorter one that we're going to reserve. We're going to call it Y. I'm going to borrow an orange color again because your book makes this kind of orange. So we'll borrow that and call that the Y tile. And let's make this a black color so I can zoom in a little bit. We'll call this tile a Y tile. So this is a Y to the first power, understood to just be a Y. So what do we have? We have X squareds right there. We have X tiles, and we have Y tiles. And they're the shorter rectangles. Now, why are we doing that? What do we have in mind? Well, we're going to set them up, and we're going to make an interesting pattern. We use something called the area model, and if you remember, when you work with area, you have length times width. So these tiles we're going to use that way. A naming convention that's really important, something that you need to be, oops, don't want to be editing my toolbar, thank you very much. One of the things that we want to be working with here is, just have to get my toolbar back. There we go. Dark colors, or any colors at all, we'll consider to be positive. So these are positive, and an absence of color we'll consider largely to be negative. And I'll explain this one when we get to it. Okay? So we'll get going with this. What we've got is, and if I have to introduce some color, I will. In the case of a Y tile, I'll do that. When we have, let's change our color up to a nice blue. These tiles here are considered to be X tiles, and because they're darkened in, they are obviously they'll be considered to be positive. These up here are considered to be negative. So they're, zoom in a little bit. So let me just go along this edge. See the length of this edge? That's the same as the length of this edge. And just for the purpose of illustration, I'll change the color. There we go. Oop, not orange. Ooh, don't use that one. Let's use green. This edge here is the same width as this edge here. So what we've got is X for height and X for width. That's why these are squares, right? They have the same width and they have the same height. Now, this one here is negative. We know that a negative times a positive, when the signs are different, a negative times a positive, remember this old rule, the negative wins, unfortunately. This is an X squared. Okay, we see that it's a square, so they're square, I get it. Okay, square. But it's negative. It's because it's a light color. So we have a negative X squared here, a negative X squared here, and a negative X squared here. It turns out that when you set up these tiles like this, x tiles multiplied by x tiles, they make squares. Okay, so they're checking to see if you set this up with, let's borrow a red color. There we go. Put in a dividing line here and here. So in this case, we're multiplying in what we call sort of a monomial statement. The expression for this, just so we're clear, let's go with a nice blue, is we have negative 2x. Actually, let's go back. Let's go with the positives first. We have 2x's being multiplied by negative 2x's. So what do you get? If you look at the answer, right, the rectangles when multiplied, if they have the exact same side length, we get 1, 2, 3, 4. Well, we have 4 what? Well, we have 4 squares. So we say, okay, we have 4. The coefficient's 4. That's how many? And it's negative. The color is a light color. So we say, well, there's 4 light colored ones. So there's 4 with a negative value. And we say we have negative 4x squareds as a result. Okay, so that's our answer. We can use what are called algebra tiles lined up this way to create shapes, and then we look in the middle. We look right here in the middle, and we say, better go with our sort of our standard yellow color. Turn that down a little bit. We look at our result in here, and that's our product. And by reading our product, we can say what the answer is as a result. Let's zoom in on this here. Now, this is an interesting example. They didn't show this with orange, and I wish they had, because your book definitely does. An orange color here, remember what I said before, sometimes we have variables like x and y, and we need to make them a little bit different. So we said that an x was a sort of the longer black rectangle. Let's just leave it at that, okay? So what do we got? I was using a green color with this before. So here we have x to the first terms. There's 3 of them. So this really represents 3x. And I'll just move this over here. And then down here, we have 2 of these shorter rectangles. Well, if those are supposed to represent y's, let's choose the orange color. I know what happens when I do that. I have to say, done. I have to choose a new color. Okay, so let's go back to orange. There we go. This represents 2 of the y to the first terms. So what do we get? Well, the height is y, so it's only that tall, right? These rectangles are a little shorter, and the width, let's use green, the width is a little bit different. So if I highlight that in, you'll see that's a little bit, the x's are longer rectangles than the y's. So I like this color coding that I'm doing. You could feel free to use pencil crayons for the purpose of this lecture. They try to do this in a black and white way, but since I'm working on an iPad, I think it's really useful to do this. So what have you got? You've got y for height and x for width. So just labeling this, if this is y for height, oops, undo. Say this is x, and hit done. There we go. I'm going to zoom in so you can see this clearly. If it's x for width and it's y for height, then these are x, undo. These are, let's just choose a new color here to represent this. These are x, y's. There we go. You could say y-axis, but we try to kind of keep it alphabetical. Again, we're looking at, remember, the width times the height. This is an area model, right? So the x times the y gives us an xy. What is that? That's kind of like an imperfect square. It's really a rectangle, right? So we have an xy here, and we have an xy here. They're not squares. You got to understand that. If they were squares, they would either be y times y, or they would have been x times x. For something to be a square, its sides have to be the same value. In this case, you can see that they're a little bit longer than they are tall. So let's get rid of that extra data there. So what do we have? If we take 3x and multiply it by 2y's, we get 1, 2, 3, 4, 5, 6 of the x, y's. Oh, let's undo that. 6, and I'll make my x look like that. I like the sort of the curvy x. You don't mistake it for a multiplication sign. Interestingly enough, if you went to solve this the good old-fashioned way, 3 times 2 equals 6, and x multiplied by y sits as, well, there's the 6, x times y. It's just waiting to happen. We just don't know what x and y are. So we can write out the expression. If you want to multiply 2y times 3x's, for your final expression is 6xy. Okay, so what do you get? You get these examples where they say, set this up with a model and make it happen. It's actually just about this quick. If dark colors represent positive value, then we'll do this pretty quick. I'll draw a little smaller. So we've got, let's zoom in. Oh, undo. Haha, there we go. This gives me, zooming is nice, gives me a little bit more room to work. So minus 3x's. You got to look at that. That means they're going to be white, and so are these. So 1, 2, 3 rectangles. Now x's are thin kind of rectangles, and let's be, oops, let's choose a red so that we can do this. So since it's the area model, you're basically multiplying the uppy downy by the lefty righty. Okay, so length times width if you want to think of it that way. And this time I'll use blue. So we've got our negative 3x, and now we'll set up our minus 2x. Try to make them the same size. So what do we get? We get squares. But what we know about negatives is 2 negatives when multiplied cancel. So these have to be colored in. So we can just color them in with the blue color. It really doesn't matter, to indicate that the squares are positive. So you sort of stop and you say, okay, how many squares do I have, and are they positive or negative? Well, you've got an x squared here, an x squared there. I'll just label them all. How many did you get? Well, it turns out that you've got 6 of the x squareds. So the coefficient 6 is a counting value. It says how many of them you have. You have 6 of these squares. Okay, not bad. I'll give you a chance to take this one on. It shouldn't take you very long. Hit pause right now and see if you can set this up the same way I do. Okay, if you've come back, I'm going to set up my x positively, and I'm going to set up, try to keep them the same length. A little hard when you freehand it on an iPad, but you get the idea. Okay, so they're all positive values. And moving along, we'll just make, since it's area, length times width. Think of it this way, length times width is what we're doing. What is the result? Well, we have x multiplied by 4x. To be really thorough, let's grab this. This is our x, and there are 4 of our x's here. One here, 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 and here. They're all positive in value. So the final result, if something has x height and x width, that means the width and height are the same, right? Okay, good. Then our squares show up. They're squares made out of x's, right? Whatever the sides are, they're the same. These are both positive, so our two positives when multiplied make a positive, right? 2 times 3 when they're positive give us positive 6. So what do we get? Well, need to choose a new color here. And what we get, I guess I could use, let's do this. You get 1, 2, 3, 4 x squareds. So your answer to this is equal to 4x squared. Not bad. Not bad. So you'll get better at doing these models. Just remember that x's are the longer, thin rectangles, and the y's are the shorter ones. Even if you don't have color, the shorter rectangles will use to represent y. So once you see this, you say, okay, there's a rule. When you multiply a monomial by a monomial, and above it was x, which it was just one thing. Let's go back to our little tool here. You've got an, there we go. You had an x multiplied by a 4x. Those are monomials. They're just one term, right? Like x all by itself. And over here, you've got another 4x, like a group of them. And you say, okay, so what is that? When you multiply a mono by a mono, you multiply, first of all, the coefficients. And you might not have seen that. But what, right? What, pray tell? Oop. And that is known as a crash. I think I should still have it, so I can sneak in again. Did it panic on me? Oh, good. We still have it. So, above, go back to the pen tool, and I'll just choose a nice dark color here. You had 1x being multiplied, the dot for that, by 4x. If there's an x, there has to be at least one there. It had the 1 being multiplied by the 4, and if you were paying attention, what really happened was the x's got multiplied together. That's how we got squares. Now, when you do the area model, you can see that there are 1, 2, 3, 4 squares. The area model is really useful because it can help you to understand how you get these answers. It's just a tool. You won't use it forever. You multiply the coefficients, and then you multiply the variables, in this case above 1x times 4x, you multiply the x times the 4x, and you get x squared. That followed the exponent rules, which I'll just write this way. X to the first times x to the first is equal to x to the 1 plus 1 x squared. That was what was going on up here. Interesting. So when you look at this, you say, okay, so you've got this area model. We're going to use shapes to figure this out. Turns out it's quite useful. Works very, very well. I had a group of grade 9s multiply not just monomials, but they were multiplying polynomials, many terms with many terms, and they were able to use that area model with shapes to get the answer. Now that's without having ever done what we like to call the straight math, just using the numbers and the exponent rules. That's the old way that we used to do it. It still works. It's all I ever learned with. But once I was shown the area model, I was pretty blown away with all these little shapes, what you could figure out. So, what have you got here? If you do this with what we call the straight math model, you could say that you multiply the coefficients. So -4 times 2 is -8. Let's switch the color to brown. And you've got the x times the x, which is good for x squared. Same pattern here. 3 times 7 is 21. And the y times the y is y to the second power. Let's see if you can pick up on what I'm doing here. I multiply the coefficients and then I multiply the variables. Change this color to, I don't know, let's go with, I don't want brown. I've had it with brown. 5 times -3. You got to pay attention to that. That sign matters. You get a -15, and then you have x times y. Well, if you don't know what they are, you just leave x as x, and at some point you're going to multiply by y. Maybe they'll tell you that x is 2 and y is 3, but we know that the final thing that we're looking at is -15 times whatever x is times whatever y turns out to be. It's okay, it's all right, it's a formula. 6 times -0.2 is, well, 6 times 2 is 12. I think of that. And then there's one item behind the decimal. So here's a little trick. Write the number 12 and make sure that you have one item behind the decimal. M times m, m squared. And make sure that your answer is negative. Okay, that's multiplication. Got to be aware of that. 2/3. Now I want to write a little bit bigger here, and let's change colors just to keep going here. 2/3 of some number multiplied. Actually, I want to even. That's okay. No, we'll roll with that. Times 12n. So you could think of this in the early going. Say, okay, this is 2/3 times 12. Nobody said a coefficient couldn't be a partial amount. 2/3 times 12. Can you figure that one out quickly? Because it's 12 over 1. Here's an interesting little canceling trick. 3, if you take the greatest common factor of 3 and 12 and divide it out, if I divide by 3, then this becomes a 4, and I get 8. 4 times 2 is 8, and then I have to multiply those n's, right? So you get 8n squared. Not bad. And the answer is positive because the factors, the things that got multiplied, were positive. Okay, so That is when you use the symbols, right? The symbols, the numbers, without drawing any of the diagrams, like what you see down here, right? But of course, revenge of the diagrams. Let's see if you can do this backwards. Think about it this way. If, let's say, 2 times 3 gives us 6, then I should be able to, let's see, 2 times 3 equals 6. Come here, you. There we go. Then if multiplying works forward, then 6 divided by, well, let's write that correctly, then 6 divided by 3 should give me 2. So these here are the factors. So if one is missing, then all you need to do, switch up our pen tool color, seem to like to do that. Let's go with that one. You've got an x squared, an x squared, and you realize you have 4 of them. And here, you know that you have an x and an x. Well, what shape made that edge? An x. So then what shape's going to make this edge? Oh, probably another x. And since the answer is positive, it must have come from 2 positive factors. There we go. So, and if you want to check it with symbolic math, 2x times 2x gives you 4x squareds. Check. Correct. Over here, I know that the rectangles, right? We know these are x's. Now, if this is white, I sort of think about this for a sec. If that's white, it's negative. Those x's must have been multiplied by something negative. Oh, these guys over here. There you go. That's how you got these negative x values in the middle, but they're appropriate. Sure, these are x squareds, but since they're white, they only got that way because this is negative, right? It's white too. So let's do that. These are negative x squares. They're white. And how many? 1, 2, 3, 4, 5, 6. Negative 6 x squareds come from the statement negative 2x. Now I'll use parentheses these times. Multiply by 3x. And again, if you multiply the coefficients, let's switch colors here. Black. Ha, hate it when I do that. You got to hit done to switch the colors. Oh, well, get over it. Negative 2 times 3 is negative 6, and x times x is x squared. Negative 6 x squared. So multiply the coefficients, multiply the variables, and do the exponent rule. It keeps going back to the same thing over and over again. Hopefully, sinking in for you. If you want to do division and you don't want to use the symbols, there is an easier way, I promise. What is, well, let's actually, before I do that, let's rewrite this. Another way you could write this is 8 times x over 4 times x. Now, what if you look for things that could cancel out, things that are have factors of each other, greatest common factors of each other? First thing that should strike you is that there is an x over an x. Well, that's going to cancel out. That's like saying 6 over 6. Okay, 6 divided by 6 is 1. So you take out the old pen of doom and you say, that cancels. How many times, if you had an 8 over a 4, you'd say, okay, well, that's just 2. That's because if you take out the greatest common factor, if you divide by 4, you get 2 over 1. So this becomes a 2, and this being a 1, well, okay, we'll just go ahead and write it. You're left with 2x over 1, which is just 2x. You can just forget if it's over 1, you can just forget the bottom part. Okay, so 2x. Here's your proof. Your answers should multiply, right, to give you the top. And do they? 4. So let's do what's called a check. Does 4x times 2x equal 8x squared? Yep. 4 times 2, 8. X times x, x squared. It's nice to know when you're right. Okay, Mr. Bleecker, is there a faster way to do this? Okay, I'm not going to take that long to do it. Absolutely, I wouldn't expect you to take very long to do it either. Let's grab a new color. I'm thinking going back to good old purple. I like to do this. Now, you can only do this when the values are all being kind of multiplied by each other, right? It's 6 times x times y. Well, that 6 is right over a 3. And since this is all multiplication, on the top, 6 times x times y, and the bottom, 3 times y, I can see that there's some things on top that are similar to things on the bottom. 6 divided by 3 is going to give me 2 over 1. And the y's are going to cancel out. They're the same value. That's going to leave me with, make this a 1, make that a 2. That's going to leave me with, there we go, 2x over 1. Okay, there's a quicker way to write that. 2x. Because you just don't write it over 1. That's kind of understood. It's going crazy. Okay, so what's the rule? When you divide monomials, we saw before that you could multiply the coefficients. Well, guess what? You can divide the coefficients and you can divide the variable terms. But what you do, as long as the variables are same, with division, remember the exponent rule is you can subtract the exponents. So you can divide the variables, and I'm going to put a little side note, and subtract if the bases are the same. Right? You can subtract using the exponent rules. Okay. Now this is where you should really challenge yourself. Can you do these? Okay, hit pause. Okay, leave it, and then come back, and I will. I'll quickly rattle off the answers to these. This. Did you really press pause, or are you just skipping ahead? If you're skipping ahead, you press pause now. Okay, I'm going to assume that you hit pause. The answer to this is going to be negative 2x. The way I think here, 15 divided by 3 is 5. The y's cancel. 5x. Three And those m's and those n's are history. Done. 8 over 12. Greatest common factor is 4. That'll become a 2 if I divide out a 4. That will become a, divide out 4, that becomes a 2, that becomes a 3. And let's just rewrite it, because I don't always have the room. 3xy over x. Just cancel out the x's. That leaves me with 3y. Not bad. Here, sometimes you might decide to go after the variables first, that if you want to write it in 2 steps. Negative 14.2 over 2. And that, there's 2 m's on the top. So one of them canceled there, and this becomes an m to the 1. What I did was m squared divided by m equals m to the 2 minus 1, or just m. That just leaves me with 1m on top. Then I can look at this. What's half of 14? Well, that's 7. What's half of 0.2? 0.1. So I figured out what that is, and then I've got the variable m. Okay, so I went through that pretty quick. That's the traditional technique, where I messed with the coefficients first, and then I went after the variables and used the exponent rule, where I subtracted right what the powers were. All right. It's quite a lengthy. This is quite a lengthy lesson, but the nice thing is it's recorded. It's online. Let's say that you're given a word problem example of this. So a triangle has a base of 12x centimeters and a height of 3x centimeters. Very important. You always, always, always draw. It said a triangle. Okay, so fine. I'll give you a triangle. So make it a little bit longer. It's got 12x, and that's what they say the expression is for the base. And we'll go like that. And we'll say the height, although not drawn to scale, of course, is 3.4x. And they say, well, what's the area of a triangle? Did you ever notice that a triangle is kind of like a rectangle that you just chopped in half and you killed off this part and you just kept this? It's half of a square. So when you look at the formula, you could just say half length times width. It's totally fair. But what we do, because it's a triangle, we're fancy and we decide to use different letters. We use 1/2 of whatever the base is times whatever the height is. Okay, so if this, let's grab our highlighter. If this is our base and this is our height, we have to multiply them, and then just because it's divided by 2, it's half of a rectangle. Well, I can do that. Even though I don't know what the final answer is, I can still do the math for this. So it's 3.4x, making a mess there. There you go. And I'll use parentheses this time, times 12x divided by 2. There's that formula in action right there. 1/2 is the same as dividing by 2. So when I go to look at the top, one of the things you could do, and it's totally fair, is you see this 2 and you see this 12? Let's reduce that. Make that a 1 and make that a 6. So that leaves us with 3.4x times 6x. Okay, so now you have to do a little bit of thinking. What the heck would that answer be? 3.4 times 6. So I'll just do it on the side here. Put down the 4. 6 times 4 is 24. Carry the 2. That's 18, 20. Ah, there we go. So when I multiply the coefficients, I get 20.4, and x times x gives me x squared. Folks, we have a couple sort of word problems to get through to finish off this topic. All right, and let's go to enter full screen. There we go. So if you've ever seen a parallelogram before, it is a rectangle sort of pushed on its side. And for our example here, they've given you the units, although it could be a little misleading. Area is always in units squared, so we've got meters squared, and for another one of the sides, we've said how long they are. This kind of a question is going to represent the side lengths with some monomials. So what have they got? Let's switch colors up. The area is 25.6 x squared, and that came from a base of 8x multiplied by something else over here. We don't know what it was. Well, when we multiply two things, we get area. Okay, so essentially we've got length times width. So to get backwards, if we know this one and we know this one, we'll have to do a little bit of division. So the answer to this is 25.6 x squared divided by the side that we know, which is 8x. And the hardest part here is 25.6 divided by 8. Okay, that's going to be 3 point, looks like it'll be 3.2. I think I'm lucky with that one. 25 divided by 8 is 3.2. And then x squared divided by x to the first, remember the old 2 minus 1, is 3 to the, or 3.2 times x to the first power. Okay, folks, very last question. This is one of those questions where you have to use a little bit of information to figure out a little bit more information. So some guy named Marco has a rectangular lawn. They've given you the area. That's kind of half the battle here. They've said that the area of the lawn is 36, I have to be careful here, x, and it's in meters squared. So what is this missing side? Because it'll help us figure out this circular patio that apparently he wants to make. Well, if 9, now this is in meters, so I'm just going to, I'll simplify the calculation. Since area is equal to length times width, our area, which is 36, represented as 36x, came from length times width. So we have to take one of our factors and use it in division. This times this gives us area. So since they gave us area, we have to divide by the one factor that we know. Here's an example. If the area of something is 6, and we know that one of the sides is 3, we'd have to divide those two to know that this was that value, 2 units. So just undo that, just to give myself a little more writing space. So this missing side over here can be expressed as 36 divided by 9 is 4, and there is an x still sort of hanging out there. So there we go. So again, if you want the proof, 36, oops, let's undo that. 4x times 9 is 36x. So we've confirmed our area. So if you know the product, you can divide by one of the sides and you get the other side. Let's undo that mess. There we go. The real part of this question, once you figure out the missing side, just using a little bit of division, you know that this circle has to be as wide as that there, which we said is 4x. Well, the idea when you do area of a circle is equal to pi r squared. Okay, so radius is half of the diameter. Half of 4x is 2x. So if we say that pi is equal to 3, because that's a pretty easy unit to use, we can solve the question. When I looked at this question initially, what occurred to me is we didn't have anything for the radius. So you can't figure out the area of a circle without knowing what the radius is. So we went right after figuring out this part right here. And it was just simple division of these two. Switch colors up a little bit. So area is equal to pi, so we'll use 3 for pi, and we'll multiply that times the radius squared. The radius is the expression 2x. Okay, no problem. Multiplied by 2x squared. This can be written as 3 multiplied by 2x multiplied by 2x. Now you could have done that a little quicker, but I just showed you the full answer. So that's 6 times 2 is 12, and x times x is x squared. So what you're left with is that the area is equal to, we'll just kind of make this clear. If you're going to use 2x as the radius, so we can go ahead and say that the area is 3 times 2x squared, which simplifies right down to 12x squared. And what gets a little confusing, I guess, is you're like, okay, if they would tell me what x is, I know the answer. They haven't told you what x is, but we know that it would be in, and I'll write this just in the actual word. So this is what it would be for area. It's in meters squared, so as not to confuse. That last example is a bit of a doozy, but folks, I think you can figure it out because expressions are just, well, they're just formula work. And since we can divide coefficients, we can deal with them. And when we apply the exponent law, as we did when we multiplied these x's here, we can just keep hammering out these expressions. If someone came along at the end and told you what x was, you would know the exact value. Right now, just consider that it's a formula, right? And you're kind of in a holding pattern. Okay, ladies and gentlemen, that's example 9, and I'll let you get going on the assignment. Hasta luego.